Are you struggling to simulate a grounding system? Today I'll show you how to do it step by step in COMSOL Multiphysics. My name is Mohammed, and in this video we'll walk through grounding resistance calculation in COMSOL Multiphysics. By the end of this tutorial, you will be able to set up and configure a 2D Axisymmetric model in COMSOL using the Wizard, design and modify a grounding rod geometry, define new materials, terminals and simulation parameters, calculate essential parameters like system impedance and step voltage, and create and customize advanced plots. Let's get started. Hi everybody, in this video I want to talk about how to calculate the resistance of a grounding electrode or a grounding system. Let's first speak about the theory. In this picture I have drawn a part of the ground. This is a pole and this is the grounding rod which is buried in the ground, and this is the connecting wire. You know that the soil has a conductivity. Therefore, the current can penetrate through the ground. Here you can see in the sketch that the current comes here, goes through the grounding rod and distributes within the ground. This system shows a specific resistance, and this resistance is very important for some kind of functions in the power system. The grounding resistance is defined as the resistance from this connecting point to the remote ground, a ground that is located far from this electrode. If we want to measure the grounding resistance practically, we create another electrode, another temporary grounding electrode in the far distance, and we exert an electric potential between these points and measure the amount of current that is fed through the ground. Here I want to show you how to calculate the resistance of this grounding system in the COMSOL Multiphysics. Just similar to a typical resistor, if you exert an electric potential between these 2 points, a current will flow through the resistor or this circuit, and the resistance is calculated as you see here. R equals V divided by I. I want to do the same thing. I want to sketch the geometry and feed the current through the grounding electrode and then see how much electric potential is created on that electrode. If I feed only 1 ampere to the ground, the amount of voltage drop equals the grounding resistance. Okay, let's go now to the software. Here in the model wizard, because I want to simulate a rod, I go through the 2D Axisymmetric. The physics that I want to use is here under AC/DC in electric fields and currents. Here I use EC or electric current as previous, then go to the study section, and because I want to measure the grounding resistance at 50 Hz, which is a single frequency, I just select the frequency domain and click on done. Okay, first we should sketch our geometry. I let the unit length to be meter, come here, right click, and we need a rectangle. This would be our rod. I set the width to 0.5 meter, which is 5 centimeter, height to 3 meter, 3 meter, 6 meters is typical values of the depth of a grounding rod, and I set the base into the corner at the radius of 0, and the Z should be -3. If I click on belt selected, you can see the rod here. You can see that top of the rod is at Z equals 0, and I have supposed that Z equals 0 is the surface of the ground. Now we want a very large amount of soil or ground around this grounding electrode. For this, I come here and select on square. I'm creating a square with the length of 10 meter and set the corner at the radius of 0 and Z equals -10, and click on build selected. If you see this kind of showing, just come here to geometry and deselect sketch, and you can see the domains. Okay, this is our grounding rod. You should in your mind revolve this system around this axis, which is the axial symmetry line. And this is the ground area around our electrode. We know from the theory that the measure of the voltage drop and the current density occurs within a limited space around any electrode system. Therefore, 3 or 4 times bigger ground, I think, is enough for the calculation to be valid and accurate. Our grounding system has a depth of 3 meter, 3.39 meter. I have selected an area that is greater than 9 meter. Before finishing our geometry, there is another point that should be addressed. Here we have a sharp point within our geometry, and this is not good because it creates a very large electric field. Therefore, we should fillet this point. I come here in the geometry, select fillet, select this point, and for example set the fillet radius to 1 centimeter and set build selected. Okay, that's good. And now our geometry is finished and ready to assign the material properties. Okay, I come here to the materials. We need one material, which is our grounding rod. This is normally copper. Therefore, I right click here, add material from library and search copper. Okay, I come, there is too much of copper here, but the things that I need lies beneath AC/DC. I select this one, copper. Now all the area are set to copper. I need another material for my soil. I click on blank material, and first I set my material to the grounding system. As I assign this material to one domain, the required properties just show up here. I set the electrical conductivity to 1/200. This is a soil with 200 ohm meter special resistivity, and I set the relative permittivity to 20, which simulates a moderately wet ground. Okay, everything is good. I just want to rename it to soil, and we are good to go. I close the geometry tree and also the material tree. Okay, for feeding 1 ampere through this electrode, I should define it as a terminal. I come here, right click on electric current. Here you can see the terminal, and notice that we have 2 terminal conditions. This is boundary condition and this is a domain condition. I'll select this and select my rod. Very well, and I set it to 1. 1 ampere is fed through the ground. This 1 ampere should comes to the ground. I set this wall and this wall, these 2 boundaries, as ground, and the surface of the ground should be set at a boundary that the current cannot go through or come inward. For this, I just select the grounding boundary condition, set this one and this one to ground, and let's see, we have an electrical insulation boundary condition here, and this is exactly the thing that I want. If I look at an equation, you can see no current can penetrate through this boundary. This is the main thing that I want. The current should comes through this grounding rod and goes here and here, which simulate our remote ground. Okay, now we need some kind of meshing system. I set it to extra fine. We are very good. Now I set the parameters of our study. Now I only want to study the grounding resistance at 50 Hz. I should also say, because we are running in the frequency domain, in fact, the grounding impedance are calculated. Okay, we are good to go, and I select on compute, but beforehand, don't forget to save your model. Okay, let's compute. Very well, now the solution is ready. I just close all of these points. As you can see, you have a voltage drop. Here is a ground, therefore the voltage is 0. And here the maximum of the voltage drop, which are shown here, is 43 volts. Because I have fed 1 ampere the grounding resistance of this electrode is exactly 43 ohms. But just I have said earlier, the amount of grounding impedance is 43 ohm. We want now to see how much of this 43 ohm is the resistance and how much is the capacitance, because our soil also has a relative permittivity and acts as a giant capacitor. Okay, I come here to the derived values, select a global evaluation, and here under the electric currents you can find here the terminals, and you can see here the automatic impedance. I just select on it and select evaluate. You can see that the main component of this impedance is a real part which represents the resistance. Therefore, resistance of our grounding system is 43.7 ohm. The imaginary part represents the capacitance value of our grounding system. Capacitive impedance of our system is 4.8 to the power of minus 4 ohms. As you notice, the imaginary part is negative. It should be so because we know that in a phasor system, in a continuous sinusoidal situation, the voltage of a capacitor should follow the current by 90 degrees, and this is minus J or minus I in a complex system. Let's look at our electric field norm. As you can see, the amount of electric field around the electrode is very high because the current density here is very high. But as you go further, you can see that the amount of electric field becomes lower and lower. For this, we can sketch a very interesting diagram. I want to sketch two things here. First, the electric potential, and then the electric field along this boundary. Please notice in our previous videos, we have defined a cut line and plotted a variable along that cut line. Now I want to plot a variable along a certain boundary. For this, I come to results, select 1D plot, right click and select the line graph. Here you can see selection. Because we don't have a cut line, we should select a boundary that along that boundary something is plotted. I set it to manual and select this boundary, and it is automatically set on voltage. Therefore, I just click on plot, and you can see the diagram of the voltage drop along the surface of the ground. As you can see, the major of the voltage drop happens within 2 meters from the electrode, and as you go further, the amount of this voltage drop goes lower and lower. Using this diagram, very simply, you can find the step voltage that happens on the surface of the ground. This is also a very important evaluation parameter for the grounding systems in high voltage substations and so on. For example, here, if someone stands here, one foot is on 10 volts and the other foot is on, for example, 2 volts. Therefore, 2 volt voltage drop happens between the two legs, but this is 1 ampere. 1 ampere exerts 2 volts. If 1 kiloamps go through the ground, this 2 volts becomes 2 kV. It can be dangerous for people. Okay, I come here and select the replace, come to electric currents. Under the electric, select the electric field norms and let's plot it. As you can see, the amount of electric field around the electrode is very high, but drops much more when you go further from the electrode. The next point is that when you are in the 2D axisymmetry, you have a very interesting option, and this is called the revolved geometry. If you click on this, you can see a revolved 3D geometry, and it seems quite well. Let's work a little bit on this. If you want to change the amount of this angle and at what angle the revolve starts and when finishes, you can come here under the data sets. Here there's an option called revolution 2D, and in the revolution layers you can see the start angle and the amount of revolution angle. If I set, for example, this to minus 35, you can see that it rotates. If I set to minus 47, for example, it comes here, and this is the amount of this angle. For example, if I set it to 270, it simulates 3/4 of a full circle. I set it to minus degree. That's quite good, and then I come back here. The plot is updated, as you can see. You can change this 3D plot as you want. I want to sketch the flow of the current in this system, and also isosurfaces that models or shows the electric potential in space. For this, I just come here, I disable the volume, right click, there is an option here says Isosurface. I just plot it just like this. You can see some kind of surfaces that by color shows the amount of electric potential. Here, for example, the electric potential is 39 volts and so on. I want them to be a little bit more apart. I just come here, and in the interactive you can just work with this to have fewer or more plates, and you can also work with this, for example 8. There would be much more of these surfaces. I now want to show also the flow of the current through the system. I just come here and select the arrow volume, and here it is automatically set to the current density in the R component, V component and Z component. Okay, now let me plot it. As you can see here, the flow of the current also can be seen, and here you can also work with this option. For example, change this into 15, and you can see that the amount of them becomes more or less. And you can also set the arrow type, the arrow length. It could be normalized, you can see it all, or it could be logarithmic, because the amount of current is very high here and very low here. You cannot see the current flow just far from the electrode, but if you set it to logarithmic, you can see the current flow all over the geometry. Now let's see what happens when the system operates at higher frequencies. I come here at this study and at the frequency domain and set the start point as, for example, 1 Hz. Let's set it to logarithmic. The stop point, for example, 10 megahertz and 10 step per decay. I click replace and compute again to see the results over frequency. I want to study the behavior of the resistance and capacitance of grounding system versus frequency. Therefore, I just come here on the results, add a 1D plot group and set it to global. I set the x-axis to the hertz, to the frequency. It is automatically set by the software. I come here in the electric currents, and in the terminal you can see here the impedance. The impedance is a complex number. Therefore, I go here and use an expression. This gives us the amount of real part of the impedance, which represent the resistance. I just plot it, and you can see as the frequency goes higher, the amount of resistance drops. We can also come here at the 1D plot group and set the x-axis to log scale. You can see here that the amount of resistance remains the same until around 1 megahertz, and then it drops very fast. Now we can set another global and set the expression here, electric currents, terminal impedance, and I want now the imaginary part, which is the capacitance. I set it to plot. You can see here the amount of imaginary part, because the impedance of a capacitor equals minus J divided by omega C. I just put a minus here so that the amount of capacitive impedance becomes also positive. If we want to plot both of them at the same axis, I set it to 2 axes, and here you can see here that the blue one represents the resistance and the green one represents the capacitive impedance. I can make it a little bit better. If you come here, you can see show the legend. The legend is at a bad situation, bad position. I set it to middle left. That's better. You can also come here and set a description. Here is resistance, and you can see that the resistance is shown here, and here would be the capacitive impedance of the system, and you can see that amount of resistance drops, but the amount of capacitive impedance just goes higher and higher. This tells us that when a grounding system operates at a high higher frequencies, the greater proportion of the current is the displacement current. It does not flow as a conductive current through ground. Rather, it operates as a capacitor, and the epsilon of the soil becomes more important at higher frequencies. As the final point, you have seen here that I have used some kind of functions here like image for the imaginary part. If you want to find the rest of it, just come here in the reflex expression. There is a category here called built-in. You have different groups here. For example, these are physical constants. For example, Faraday constant or I don't know, Boltzmann constant, K underline B underline const is known by the COMSOL Multiphysics. These are operators, and here you can find the mathematical functions, and under the basic, here you can find the absolute value, the phase angle, the imaginary part, and many other functions that you can use in the software because they are predefined. Okay, that's enough for this video. In my next video, I want to show you how to account for the skin and proximity effect in calculating resistances. If you have found this video helpful, please just like it so the other people can also find it. And moreover, if you have not yet subscribed to the channel, please support the channel and video by your subscription. I'm looking forward to see you in my next video. Take care and bye.